Okay, we're going to continue the talk about motion planning by talking about road maps today. So, first, let's just recap. So, with no obstacles, path planning is just a control problem. So, find the function that moves the robot to the goal and that considers the dynamic constraints of the robot. But we saw that with obstacles, lots of issues arise. So, we don't really know how to switch the paths, and we don't really know how to balance path optimality and safety. So what we came to is that it's probably best to just discretize our space somehow and then use graph search. And when we use graph search for motion planning, the nodes of it represent the states or the configurations. So those could be like XY, or they could also be like XY theta. And then the edges represent the motion commands to actually move from state to state. So I made a video of me performing A star on some example grids, and I'm going to show that video now. Okay, so I just want to go over my A-star implementation for ROS paths. I'm not going to go over the whole script because my AI class is implementing A-star currently, so I can't give away all the answers to them. But just keep in mind, I have a very standard A-star implementation with very little optimizations, but not deliberately going out of my way to make things slower. I'm just using the heap queue library for my priority queue, and I'm just otherwise I'm just using list. So when this runs, this node is going to run this class A star, and it's going to spin indefinitely. It's just going to wait for things to be published. It's waiting for things to be published on map, the topic called map. And when that happens, it's going to call this function here, grid callback. So message is going to be our map, and then it's going to set the grid, set some grid info. It's going to say we're running A star, and then it's going to do this informed search function, which I'm telling it to do A star. It's going to time things, so it's going to see how long it takes to actually run this. I'm going to pass in the grid that we got through the topic, and my start is going to be 1, 1, and my goal is going to be 99, 99. So the grid is going to be 100 by 100. So then whenever it's done, it's going to print the runtime, it's going to print the number of nodes we expanded, and it's going to print the final path. So we will just start running that. And then over here, I've got this node that's going to generate a map for me. So it's going to publish onto the map topic. It's going to publish an occupancy grid. So I start by creating a random grid, and then if I want to, I can create some random obstacles. I just set the width, the height, and the X and the Y. But right now, I've commented this out. So this function here, set random rect ob, that would actually create the obstacles in the grid. So it would like change all the pixels to like be occupied where the obstacles are. But currently I'm not doing that. I'm just going to work with an empty grid, and it's going to be size 100 by 100. Here the resolution is 0.05 meters, which is 5 centimeters. So this is not just come up with, it's not like just a magic number that I came up with. So 5 centimeters is generally agreed upon as like the default resolution for occupancy grids. So when you work with mobile robots, pretty much all of the main mapping packages, whenever you like map out your environment, it returns to you a map that has a resolution of 5 centimeters. And for reference, 5 centimeters is like a little over 2 inches, I believe. So we have a 100 by 100 grid. This is going to correspond to a 5-meter square in real life. So the thing that we're planning on right now would correspond to just a 5-meter square that's empty, full, no obstacles on it, and we're trying to plan from one corner of the square, index 1, 1, to the opposite corner, which would be 99, 99. Okay, so I'm going to publish this. I'm going to run this node. And then we're going to go back here. If it says it's running A star, and let's just see how long this takes. So I have this visualization open while we're waiting for this. This light gray square right here, this is the 5x5 square that we're planning on. Okay, still not done. Okay, there we go. So our runtime was about 24 seconds. It expanded almost all of the nodes, so this would be like 10,000. 10,000 is the total number of nodes in the 100 by 100 grid. So we almost expanded all of them, and then it's going to print the final path here. Okay, so the first thing that you should probably be thinking, certainly the first thing that I am thinking, is holy crap, that's slow. 24 seconds to just plan 5 meters in the real world is a really long time. I mean, can you imagine if every time you wanted to move 5 meters, you had to stop for 24 seconds and think about how you're going to move there? So, you know, the thing that I'm trying to get across here is that this is very slow. And we can do some things to make it better. So the state space size is pretty high because we don't have any obstacles. If we had obstacles, then we would have fewer nodes to expand. So we can try to put this function call back in to actually create the obstacles. So there's a bug in my code that I don't feel like figuring out right now. So let's see if this actually works. And if it does, I'm going to switch to RViz real quick to show you. Yeah, okay, cool. So now our map has these black pixels that represent the obstacles. So these are just kind of randomly defined by that node. Did I have this running? No, I didn't. Okay, so we gotta run this again. Okay, so now we're gonna publish another grid, 100 by 100, that actually has obstacles in it. And we'll see how long this takes. It should be faster. I'm not sure how much faster though. We can take a look here. That's what we're operating on. Okay, so 13 seconds. So, you know, a bit faster, almost twice as fast, but still not really within you know, an acceptable time to where we would say, oh, okay, we're planning pretty fast now. 13 seconds is still pretty slow. Let's do it again. Okay, let's see what it looks like now. Now this is what the map looks like. I was running A star again. Okay, 12 seconds. Okay, so it's still expanding a lot of nodes, still getting a very long path. So 12 seconds, you know, I mean 24 seconds was already bad. 13 and 12 seconds is also pretty slow. So if we were to increase this to go up to just 10 meters, you know, we would be looking at not just double the time, it would be an exponential increase in time. So keep in mind that when we're using these graph search algorithms like, you know, A star, depth first search, they have exponential time complexity, not linear. So, you know, it's unlikely that this would probably, you know, finish very quickly. Probably longer than I want to sit here and just, you know, wait on. And when we can get up to 400, you know, it may take, you know, an hour or something to finish. So, you know, these spaces still don't really correspond to very large spaces in real life, right? So a 200 by 200 square would only be 10 meters. A 400 by 400 square would be 20 meters, which 20 meters, okay, that part is kind of getting up there, but, you know, it's still not really like a huge distance. So what this means is that using graph search algorithms themselves are actually not that good because they're very, very slow. You know, whenever we're using occupancy grids, which in mobile robotics, we are almost always using occupancy grids. At the very least, that's like our raw data that we're getting from our like sensing package. Trying to just do graph search on an occupancy grid is going to be way too slow. If we had an environment where nothing ever changed, you know, like a totally static, we know everything about the environment, then that would be fine probably. But, you know, what makes robots hard is that there are dynamic environments, or we don't know everything about the environment. We have to sense as we go. And when we start encountering all these problems that arise in motion planning, 20 seconds, even 12 seconds to plan is just like, very, very slow. That's like glacier speed. So, for the rest of the PowerPoint that I'm going over, we're going to talk about ways to kind of speed this up. So what we saw was that A-star was just too slow. And if A-star is too slow, that it's pretty safe to assume that the other searching algorithms are also too slow. And the reason is that we just had too many states, too many reachable states. Even when we put in a bunch of obstacles, we had way too many states to search through. Our resolution was currently 5 centimeters, and that's kind of like the default value. You can set it higher. You could set it like 10 or 20 centimeters, but then it's too coarse to be realistic. The robot won't be able to make fine motion, like quick turns or navigate between narrow spaces, things like that. The robot just won't be able to do. So we would like to keep it at roughly 5 centimeters. And if we keep it at that and we use A-star, what that means is that we just can't really handle any changes in the environment. So if our environment is completely known and completely static, it's probably fine to wait 20 seconds before moving. But real world environments are not like that. There's moving obstacles. You can find new obstacles that just pop up that you didn't see before, and they're moving. They could also just be new static obstacles. You could have incomplete information about the environment. So you might not be able to sense everything, and then once you sense new stuff, you have to replan. And it doesn't really deal with like motion error or sensing error, because if our robot deviates too far from our plan, then we probably have to replan. Or if we can't sense things correctly, like if we find that this obstacle actually isn't taking up this many cells, then we have to replan again. And so we don't want to have to sit there and wait every time that we have to do that. So what we're going to talk about today are roadmaps. So roadmaps are graphs that try to minimize the amount of states by only including a representative node, the representative nodes in a graph. So rather than like a cell where we're using every single or almost every single XY location is a node, instead we just want to like take a small number of nodes from the environment and say, hey, these are the nodes that we care about. These are the nodes that matter, and we're only going to use those to plan. So essentially, it's about how do we discretize our space more efficiently. If we can make it a discrete environment and represent it more efficiently, then we can plan faster. So in your book, it goes over, or sorry, not in your book, but in the book that I posted, the reading, it lists 3 properties for a roadmap. So given any start position, which they label as Q start, so all their like configurations are Q. So we have some start, Q start, and then we have some goal, Q goal. We have 3 properties. So the first one is that there exists a path from Q start to a point on the roadmap, and we're going to label that roadmap point Q prime start. So that's saying that from anywhere in the environment, we can like connect to the roadmap. And then we're also saying that there exists a path from some point on the roadmap to Q goal. And we're going to label that point Q goal. And then we're saying that there exists a path from Q start to Q goal. So the first one we're going to look at is a visibility graph. So in a visibility graph, the nodes are the vertices of the obstacle polygons. So I've got 2 obstacles right here, and you can see that for every vertex here, it has an edge to multiple other vertices. And the edges are there if they're within line of sight of the other vertices. So take this one, like down in the lower left, this vertex here, it's connected to 2 other vertices. And that's because you can form a straight line between them and it doesn't like hit anything. So we know that they're like within line of sight of each other. So what we do is go through every single vertex on these obstacles and we connect them to as many other vertices that basically that we can, that we can connect with a straight line. So let's look at the accessibility part, which is that any start node can connect to the roadmap. So I've put a queue start over here in the top left, and I've put a queue goal over here in the top right. So when we put in queue start, we're trying to see, okay, let's connect queue start to as many vertices as we can. And those edges and queue start become part of the visibility graph. So I labeled them red here. So queue start has these 4 connections. It can see these 4 vertices. So we add edges from queue start to those 4 vertices. And then we have to consider departability. So we can reach the goal node from any node. We can reach any goal node from the roadmap. So we've got queue goal over here. And so how we do this with visibility graphs is that we do the same thing with queue goal that we did with queue start. From queue goal, we try to see what are all the obstacle vertices that queue goal can be connected to, and then we make those connections. So I also added these here in red, and queue goal has 4 connections. And so this right here is the visibility graph. So, okay, let me just cover this here. So connectivity, there always exists a path from one node to another node in the roadmap. And so in the end, this is what we get. We get queue start, we have queue goal, and we have all these obstacle vertices, and we have all of these edges. And so all of these edges and the obstacle vertices in queue start and queue goal, that is the visibility graph. So the visibility graph is the obstacle vertices, the queue start, the queue goal, and all of the edges in this environment. So now that we have this, now that we have the visibility graph, we can just do graph search on the visibility graph. So what's really nice is that, if we wanted to do this with a grid, we would, overlay a grid onto this, and we would have quite a lot of cells to search through. But with a visibility graph, we significantly reduce that. So let's see, there's 1, 2, 3, 4, 5 vertices on one obstacle. 1, 2, 3, 4, 5. So 5 vertices on each obstacle, and then so that's like 10 states, and then a couple more states. So you're talking like double digits of states, not a very high number. Whereas with a grid, you can very easily get into the hundreds or thousands. So just to compare this, the advantage of a roadmap over a grid is that we have far fewer states to search through. So in other words, the state space size is drastically reduced. And this is really nice because since we're still doing graph search, we can maintain the optimality of using A*, and it guarantees that the robot will be moving in free space. I'm going to put an asterisk on that. So the asterisk is that you can see that these vertices get really close to the obstacle, these nodes basically are the obstacle vertices. So you kind of have to account for that. Obviously, if you try to move on this graph, you're just going to move into the obstacle. So generally, when you use these, actually what you would do is like whenever you approach a node, you just have your local control kind of take care of that for you. So like your local control loop would avoid the edge of that obstacle there. And so the disadvantage of this, the disadvantage of a visibility graph, or pretty much of all roadmaps, is that they require some significant amount of pre-processing. So, we don't just get to have this visibility graph for free, right? We have to sit here and compute it. And, the naive approach, I believe, is big O n squared. But there are some algorithms that can do this in n log n. So n log n is not terrible, but it's not really that great either. So also we have less flexibility of robot control, so we may be forced to get too close to obstacles. So this is something actually that's specific to visibility graphs, not roadmaps as a whole. I mentioned that local control can take care of this. That is true, but you're still close, right? You're still going to get really close to the obstacle. So when we talk about visibility graphs, we kind of have this catch here of like, yeah, you get a really small number of states, but you are getting really close to the obstacles. So let's talk about a second roadmap type, and those are Voronoi diagrams. So these are something that exists outside of the robotics world. They're used in a lot of different fields, actually. And what they are is a way to like segment an environment. I posted 3 examples here, and each of them have a bunch of lines and a bunch of dots. And the dots are like the sites. That's what we call them, the sites, or you can also call them the centers. And each point on these lines is equal distance between 2 sites. So if you look at these lines and all of these diagrams here, each point is going to have an equal distance from its 2 closest sites. And so what that means is that each region that gets formed by these lines, so like these lines kind of enclose a region, what that means is that every single point in that region is going to be closest to the site that's at the center of that region. So how do we go from that to robot motion planning, right? So we're going to use something called Voronoi graphs. So before we were talking about diagrams, now we're talking about graphs. I put an example over here on the right. So given some environment that's full of obstacles, we're going to make a graph where each point on the graph is equal distance between the 2 closest obstacle features. And so obstacle features are going to be vertices, edges, and then the boundary edges. So here, if you look at this graph I've posted, you can look at the whole graph and kind of see that, like, yeah, every point is equal distance between its 2 closest features. And some parts are lines and some parts are curves, and it's not really that, it's kind of hard to make out which parts are lines and which parts are curves. So I put that down here. There are 3 different cases. So if you are comparing 2 edges, so that means that the 2 closest features to the point are 2 edges. If you're trying to have the kind of the axis in the middle of 2 edges, it's going to be a line. So it'd be this dotted line right here. If we're doing vertex to vertex, so the 2 closest obstacle features are 2 vertices, you're also going to have a line. But if you're doing edge to vertex, you're going to end up with a curve. And so you can kind of see over here on the right, you can imagine the point where this curve, like the curvature actually changes. Like at some point, the slope here is going to be 0, right at the very bottom of the parabola. At that point, you're going to have equal distance between that point and that edge. And then as you continue with that parabola, you have to curve it, because you would be getting farther away from the vertex while keeping the same amount of distance to the edge if you did not make a curve. So that's why the edge to vertex, you have to do a curve, some type of parabola to maintain equal distance there. So Voronoi graphs are used pretty often. We still get the same advantages of visibility graphs, like the same advantages of road maps in general, because here in this graph that I've shown, you would probably overlay like a grid over this whole graph, like this whole environment, and you might end up with a pretty large grid. But if you find the Voronoi graph of this region, you can actually just remove all the cells that are not on the Voronoi graph, and then the number of states that you have to search through becomes really small. So on that note, there's a really convenient algorithm called the Brushfire algorithm, and you can use it to create Voronoi graphs over a grid structure. So I've put some examples here on this slide. There's going to be a few, like one more slide with these. How this works is that you detect all the cells that are adjacent to all of the obstacles in the environment, and then you set their value to some integer. So over here in part A, you can see that all of the cells that are adjacent to the obstacles in the middle of the environment, they're all set to 2, like all those ones that are right next to that triangle, and then that like weird oval shape. And then in addition to those, you also set the boundary pixels to 2. The reason is that those boundary pixels are treating the boundary as an obstacle, so they're considered to be adjacent to obstacles as well. Then you collect all those cells, all those pixels that equal 2, and then you go to their neighbors. And for their neighbors, you're going to set their value to 1 plus 2, or 1 plus like whatever value it is. So if you look at part B on the right, you can see we filled in a lot more cells, and they have value 3. So what that's saying is that it's kind of like saying we are one more distance away from an obstacle than this other cell. So I find it pretty weird that they started with 2, actually. I kind of wish they would have started with 1. I think it's a lot easier to understand. If they would have started at 1, then you could say, like, I am 1 distance away from an obstacle, or like I am 1 cell away from an obstacle. And then I think it makes a lot of sense intuitively to explain this algorithm by saying that the values represent the distance from the obstacles, like the number of cells. They set it at 2. I don't really know why they did that. But essentially, the values in the cells are representing some distance. And that distance is like how far that cell is from an obstacle. So if we continue, we would get all the cells that have value 3, and then we would go to their neighbors, and we would set those to 4. And then we would just keep doing this until we just ran out of cells, basically. So here on C, we've done that. So we've gotten the cells that have value 3, and we've gone to their neighbors and we've set their value to 4. Next, we would get all those cells that have value 4, go to their neighbors. If they're empty, then we would set them to 5. And we just keep repeating this process until we've set every cell in this environment. So I've skipped some steps here. So on the previous slide, I had A and B. On this one, I have C, and then I have ... and then F. So I'm skipping D and E. So we're just going straight to almost the last step here. So keep in mind that you're only changing the cell values if they do not have a value already set for them. So like right now at C, we can collect all the 4s, right? Those are the ones that we most recently changed. And we would go to their neighbors and set them to 5. But what about the 4s on the left-hand side? So see, there's like on the leftmost side of this environment, if we go right, it goes 2, 3, 4. So those 4s, of course they have neighbors, they have adjacent cells, but we already have a value for those, right? The values are 3. So we actually don't set those. And if you look over here on F, you see more of that, where we're ending up, we get all the way up to 7, but then like we did go to 6, and we didn't set all of the 4s because of they weren't always next to empty cells, and kind of the same thing with 5s and 6s. Eventually all these cells are going to be filled up. And so what's really cool is that the collisions of what they call fronts, or what other people call fires, form a Voronoi graph over this occupancy grid. So we had some grid that was just 1s and 0s, right? And then we perform brush fire. And at some point while we're doing brush fire, we reach this point where our cells have no neighbors that haven't been set, right? So my example over here on the left, all those 4s that are on the left that are surrounded by 3s, like so from the leftmost boundary, it goes 2, 3, 4, and then 3, 2. Those 4s are like where 2 fronts collide, where two like waves of this algorithm run into each other. And once you detect that, you can actually detect which cells would be in the Voronoi graph for this environment. So once you do that, then you can say, okay, well, let's just set all the other values to something like -1, or like 100 or something, and we're only going to search on the Voronoi graph cells. So we would set those cells to like 1 and have all the other cells be -1. So then when we run breadth first search or depth first search, and we expand some nodes, we check the value of those nodes. If it's like -1, if it's something that's not on our Voronoi graph, then it is not a valid state. So then, even though we're using a grid here, the number of states that we have is like drastically reduced. And what's really cool about Voronoi graphs, as opposed to visibility graphs, is that we don't get very close to the obstacles. So by definition, we are maintaining maximum distance from our two closest obstacles at all times. Because we're moving on the Voronoi graph, we know that every single point that we move on is going to be it's going to be like have equal distance from its two closest neighbors, which means that it's maximizing its distance from all obstacles. So if it were not equal distance from its two closest neighbors, it would be closer to one of them than the other, which means that its overall distance to any obstacle would be lower. So what we're doing here is saying, how do we reduce the number of states in our environment, while also maintaining like optimality of like A-star search or something, and also trying to have a safe path. And that's what Voronoi graphs give us. So again, keep in mind, we still do have this disadvantage of, these things are not easy to compute. But in general, once you compute them, you can plan on them very quickly compared to graph search algorithms. Okay, so let's just recap real quick. Roadmaps are a data structure to represent continuous spaces as a discrete space. So keep in mind, we can't use continuous functions for our paths because we would have infinite possible states, and if we try to just make a grid over it, that is an option to discretize the space, but unless we're doing something extra with the grid, then it still takes a while to do that. So roadmaps are kind of like an efficient way to represent continuous spaces while also reducing the search time of our algorithms. So we went over two types of roadmaps. Visibility graphs use obstacle vertices to connect the environment, and Voronoi graphs use the obstacle vertices and the edges to create a graph that actually maximizes the distance from obstacles at all time. So while we do get advantages here, this is not the end-all be-all for motion planning algorithms. It's actually pretty far from it. And the main reason is still the pre-processing. So it's important to go over these methods because they are better than anything that we have encountered so far, but they still may not be fast enough to deal with changing environments. So next time we're going to talk about just more motion planning algorithms. We have two more subjects to talk about. We will see on the order of them. That's why I just paused for a moment. So we're going to eventually start looking at some algorithms that we would consider to be pretty fast and can actually be used in real world applications. Okay, if you have any questions, please just email me or come by office hours. Again, my office hours are Monday, Wednesday, Friday, 2 to 3. If you see my door open, it might be okay to just come in. If I'm not busy, I can help you. Just try to connect with me in some way if you need help understanding the material.